So we've come up with a story about what happens when you get a binary star which one component is a white dwarf. You get the star which is expanding, filling its Roche lobe, spilling gas via a hotspot onto an accretion disk and onto a white dwarf. Now that is indeed a true story for about 75% of these sort of binary systems. But in this video we're going to be talking about the other 25% which are altogether weirder. It's a great pleasure to have my colleague Dr. Lilia Ferrario from Maths here at ANU, who is an expert on the other 25%. So, the other 25%, what's different about them?
Well, they are different because, as you can see, what we have here is a very large accretion disk around this white object here, which is the white dwarf. There is accreting matter, and here you will have a boundary layer, and the matter is just the accretion disk is coming all the way to the surface of the white dwarf. When we have that the white dwarf is magnetic, is highly magnetic, then the disk is not going to be able to reach the surface of the white dwarf, but it will be disrupted by the magnetic field.
So here's a picture of a magnetic field of a white dwarf.
Yeah.
So are white dwarfs typically magnetic?
No, actually, magnetic white dwarfs are quite rare. We talk about 8 to 10% of white dwarfs are highly magnetic. And when I say I'm highly magnetic, I mean with a field of about 10 to the 6 Gauss, 1 megagauss. And
Do we know what's different about those white dwarfs as opposed to the others?
well, why they are magnetic? This is a good question. There are actually quite a lot of papers now in the literature which try to explain exactly this point, why only a subset of white dwarfs are magnetic. Because if it is something that happens during the evolution of a star, then you would expect that, well, they would all end up being magnetic. So while only this is a small subset, something must be happening. So there are two theories that people are considering quite seriously. One is the fossil field theory. So they say, okay, stars are born from the interstellar medium, and some parts of the interstellar mediums are more magnetic than others. So that when stars are born in these parts in the magnetic parts of the interstellar medium, then these stars become highly magnetic. And they explain why there are some main sequence stars that are highly magnetic.
So this theory, it would all be from how the stars are born. It's a sort
Exactly,
of nature
yes.
rather than nurture. Some
Yes.
stars are born in giant molecular clouds, have lots of magnetic fields, and they keep it all
Yeah.
the way through their main sequence lifetime.
That's
Even when they die and turn into white dwarf, they've
That's
still got
right,
the magnetic
that's
fields,
right.
and other ones don't.
Other ones don't.
Just
So
born
that would
poor.
explain it. And also would explain why the magnetic field flux, the highest magnetic fluxes are the same in all these types of objects, from main sequence all the way to white dwarfs and neutron stars. But, I mean, this theory has had some problems because it's not clear how a magnetic field could survive through stellar evolution, particularly in an intermediate mass star, where, yes, the evolution is extremely, that's right, it is very complicated. So it's gone a bit out of favor. And the other possibility that people have been discussing is that of stellar mergers. So when you have two stars merging in a binary system, then the differential rotation created in the envelope of the merging object creates these very strong magnetic fields.
So in that case, these magnetic white dwarf binaries might have been a triple
That's
star
right.
system originally, and two of them merged to produce a magnetic white dwarf, and
Yes.
the other ones then
Yes.
feeding gas onto that.
Yes.
I
Yes.
thought it was complicated enough as it was,
No, things can always be more complicated in astronomy, as you know.
as in the rest of life. Okay, so what difference does this make? Here's an artist's impression of magnetic
Of
white
a
dwarf.
magnetic white dwarfs, yes. This is an intermediate polar, in fact. And, well, what we can see is that the accretion disk does not come all the way to the surface of the star. So what we have is the formation of two accretion curtains. They are called accretion curtains. And one accretion curtain that is hitting the white dwarf at the North Pole, And then we've got this other accretion curtain, which is hitting the other magnetic pole.
This is a bit like maybe the aurora of the Earth, that charged particles are funneled down the magnetic field lines.
Exactly.
Only the magnetic field here is much, much, much
It's
stronger.
much stronger, yes. Here in the intermediate polars, we talk about a magnetic field of about between, say, 1 megagauss, 10 to the 6 gauss, to about 10, 15.
By comparison, what's the magnetic field of the Earth?
Half a gauss?
Yes, so about 1,000,000 times stronger than the Earth.
Yes.
Okay, yeah.
It's a very serious magnetic field, yes.
Okay.
So, yes, everything else is like we
Yes, so
we
you still have the
that's
stream
right.
and the hot spot and the disk. The disk gets horribly traumatized when it comes close in by this magnetic field.
Yes, but otherwise everything is. When we observe these systems, we still see that there are lines that are formed in the disk, in the hot spot, but then we also see the signatures of these curtains.
Okay.
So you can see that we don't have a Keplerian motion anymore, but we have the infall of material onto the white dwarf surface.
Okay.
And they're very strong X-ray sources.
Now, there are some of these sources of magnetic fields are stronger still. So what happens there?
Yeah, things get extremely weird at this point. So what happens is that here we have the ballistic stream coming from, you are sitting on the Lagrangian point somewhere there. Yes.
So this is coming from the Roche overflow,
Yes,
falling from the other
that's
star.
right.
And
And
instead of
then-
hitting a hot spot, it hits a magnetic field.
Exactly. It hits the magnetic field. So you've got the very hot region at the base where the threading of the material occurs. And then the material starts streaming along what is called a funnel. And then what we have here is an accretion shock. So you have emission of very hard and soft X-rays, and also cyclotron emission, which we're going to talk about in a second. And this is your highly magnetic white dwarf.
So here's a view from a bit further out of the whole
Yes,
thing.
so here you can see all the various components. So again, you see your lake type star. So your inner Lagrangian point will be somewhere here, ballistic stream, but you can see that instead of having the material forming an accretion disk, you have a coupling region on the orbital plane, and then the material is lifted, it forms an accretion funnel, and it hits the white dwarf surface.
Okay, so how do these things look different? We talked about cyclotron radiation so
Yeah.
far for this white dwarfs. We talked about black body radiation,
Yes.
optically thick and optically thin. But here we're talking about something quite different. Do you want to talk us through what cyclotron radiation is?
Well, what happens is that what we have are charged particles. This is an electron, and these ones are your magnetic field lines. So the white dwarf will be somewhere off to the left. And what we have here is an electron. There is a spiraling along these magnetic field lines.
Yeah, presumably an electron that's moving. It's a moving charge, which is a
Yeah.
current. And if you have a
Yes.
current magnetic field, you get a sideways
get a
force.
sideways
And
force,
so if you've got a
yes.
particle moving with a sideways force, it will go in circles. So
That's
here it goes,
exactly
loop de
correct.
loop around
And as
there.
it goes in circles, it emits radiation because any charge accelerated particle emits radiation.
Yeah, it's just like a radio transmitter. In that case, you jiggle electrons up and down a pole and they
Yeah.
radiate, TV.
That's right.
If in this case you're jiggling it round and round in circles and it generates its...
It
What sort of
regenerates.
frequencies are we talking about here?
Well, here we talk about, the emission occurs for a typical AM HER would occur in the infrared.
Okay.
And then
So
what
that's
you're
very high
going to
frequency
observe,
compared to terrestrial
yes.
radio.
And
because
then
it's accelerating really fast as the magnetic field is so
yes.
strong.
But there will be harmonics that will be observed in the optical spectrum.
Okay, so the
of
spectrum's
these
going to look a bit
objects.
different. You want to talk us through this diagram?
Okay. Well, first of all, let me say that you don't see cyclotron harmonics in every spectrum of a magnetic system. So you have to have quite special circumstances, because if the accretion rate is very, very high, then all the harmonic features will be washed out.
Just smothered as all the stuff falls in somehow.
Yes, so you don't see anything anymore. So we are in a situation a bit like that of your dwarf novae, where what you really have is that the emission is really dominated by the accretion disk. In this case, in an AM-HER type system, the accretion,
AM
the
presumably is the
emission,
archetype of these sort of systems.
yeah, will be dominated by the accretion funnel. So this is quite interesting. These are the very first cyclotron harmonics ever observed in an AM-HER type system. And as you say, AM-HER was the prototype, the one that was first observed in 1977.
Okay.
And somebody just, Santiago Tapia, pointed a polarimeter to observe a cataclysmic variable and
This is
noticed
the type
it
of
was
spectrograph
highly,
that
yes,
measures the polarization.
yes, it was highly polarized. And so these observations were made in the late 70s on the Anglo-Australian telescope.
Mm-hmm.
And as you can see, the spectrum has these
Wiggles.
cyclotron humps.
So that's caused, each hump is caused by the frequencies
By
of
the
electrons
frequency.
spiraling around.
Yes.
And what's the spectrum at the bottom? That's the faint.
Well, this is the faint side of the star.
So this is the side where the stuff
where
is slamming
the
into
accretion
it,
shock
and that's the
is
opposite
seen,
side.
and this is the opposite side. So you can see in the opposite side,
Yeah, much
there
like we've
is
been talking about before.
yeah, there is nothing. There are no wiggles. But on the side where the accretion shock is, then we have this cyclotron harmonic
Yeah,
pattern.
we've got an infrared spectrum here showing
And
the
this
same
is
thing.
the infrared spectrum of another AM-HER type system, which is called STLMI. And this, as I said, it's in the infrared, so these ones are microns on the x-axis. And again, what we can see is this wiggle. We can see these cyclotron humps. And they can be modeled with a field strength of 12 megagauss.
Okay, so and what do you find so fascinating about these systems?
What I find fascinating about the physics is absolutely fascinating because it is something that cannot be reproduced in a terrestrial lab. I mean, this kind of magnetic fields, well, we can't have them, we can't create them on Earth.
Mm-hmm.
And so it's a quite extreme type of physics that we are looking at, something that we can only observe in space.
Now, most astronomers tend to avoid magnetic fields wherever possible. Oh, magnetic field, because they're too complicated. I mean, do you find them particularly complicated? Or?
Well, yes, they are, because obviously you do introduce a lot of complication, but you see, in most cases, you can probably avoid having to introduce these magnetic fields. After all, as we know, some 90% of stars are non-magnetic, so why bother with putting magnetic fields in? But when you start looking at this kind of objects, then you can't avoid magnetic fields. And you just have to try to fit the observations, to understand the observations as much as you can. And you have to understand the role that magnetic fields play in this kind of objects.
Great, well, thank you for coming in.
My pleasure.